guys. So today we're going to do our first lesson in R. I'll try to make this as brief as possible. So first thing we want to do is you want to open this lesson. So I'm gonna go ahead and reopen it. So you're gonna go File, Open File, and then find wherever it is in your files thing and select it, open. Cool. So the next thing you're going to want to do is follow these directions. So line 2, leave this be, author, change this to your name, change this to the date, and don't change anything else. So the next thing we want to do is we want to set the session. We want to set the working directory. So you're going to go to Session, Working Directory, choose Directory. Just choose, I usually make a folder. It's called Working Directory. And I choose that. And that's where everything you export is going to save. So basically make your working directory for your exports for them to save to it. And yeah, so now we're ready to get started. We're going to open this up a little bit. Okay. So first you can use R like a calculator. So simply type in the operation like you would an online calculator. And boom, it does it. So I have these all typed in already. So let's see what happens when I run the code. Okay, what's 7 plus 2? 9. 7 minus 2? 5. 7 divided by 2? 3.5. 7 times 2? 14. Negation. Exponent. Perfect. Everything looks good. Okay, so you can also do this for quotients and remainders. Say you want to know, say you are dividing something that's not divisible. So you want to know the remainder. To know the remainder, you simply do the double, percent sign. But if you want the quotient, you do the percent signs and then in the middle a forward slash. So let's run this and see if it's correct. So 7 divided by 2, it should be 3 with a remainder of 1, right? So this should be 1 and this should be 3. 1, 3. Perfect. So you can also use R to do trigonometric functions. But yeah, all you do is type in sin, cos, tan, or arctan, or whatever you're doing. Put in the number that you want that of, press play, and there you go. We also can do log functions, so pay attention here. Remember natural log, which is ln, which is the inverse of e. In R, natural log is just called log. And regular log, log base 10, is called log 10. This is how you do a regular exponent. This is how you want to do an e exponent, so a natural exponent. So like e to the whatever, e to the x. So we can run this, see what the answers are. I wouldn't know these off the top of my head anyways, so I'm going to assume these are correct. So the next thing, aside from, so it's cool, you can use R as a calculator basically, but that's not really what R is used for. R is to analyze data sets, and data sets can be in forms of vectors. So vectors are a combination of elements that are specific to order, and you can even filter elements in a vector, you can combine vectors, you can create vectors if you wanted to generate your own random data. You can table vectors, you can do vectorized operations to them, and so that's what we're going to go over today. So here's an example. So basically you make a vector by concatenating it with each element in the list separated by a comma. So this is a list of 1, 4, and 3.2. So if you just run this, what it's going to output is 1, 4, and 3.2 because it's just printing what you said to do, and it's you didn't give it any sort of operation. You can also make a vector out of words. So when you do it with words, you need to put the words in quotation marks. So example, make two vectors of 3 adjectives and 3 nouns. So there you go. So you can so these are kind of pointless. Like you can't do anything with a vector really complex unless you assign that vector to an object. Once it's an object, those objects are then saved in your global environment, and these objects are then known. So it's basically the vector is assigned as an object, and it's just an easy way to be like, I have this vector, I have this huge data set, and I want to do all these operations to this object. So we can make an object by simply using an arrow or an equal sign and to whatever, and then it's whatever that object is supposed to be. So if we want to assign a 4-element vector to variable a1, we would say a1 concatenate 5, 7, 3, 1, and then print. And then you want to do print because it's an object, and so while this will just print automatically, once it's an object, if you don't print, it won't show up. So let's do this. So hashtagging basically just means it's a comment and it won't recognize it as code. So let's run the code again, and yeah, look, it's gone. A1 isn't there. So once you assign an object, you have to press print in order for it to come out below underneath your code chunk, but otherwise it will always go to your global environment. So let's just run that one more time. So it pops up. Okay. So try it yourself. Make a single vector like this one, composed of at least 3 elements that when printed says morning sunshine, the world says hello. So go ahead and try that yourself. Okay, so we can also make vectors in a sequence. So say you're trying to make a large data table and you're just trying to give everything an index number. You can give everything an index number by creating a sequence. So let's say, say we want to generate random data that's like, or not random data, but you want like a distribution of a certain range or something like that, right? You want to know those values. You can use the sequence function. So you just do seek from where you want to start to where you want to end, and by whatever increment you want. If you want it with increments of 1, then you just do this, because this defaultly knows just doing the starting and the ending, the min and the max with the colon, and knows you want a sequence by increments of 1. So if you want increments of anything but 1, you need to use the seek function. If you want there to be a vector with 9 equally spaced elements, so you then you do seek from min to max, and then however many elements you want. So let's run this, see what pops up. And there you go. So this is all the numbers from 4 to 9 with increments of 1. This is all the numbers from 4 to 6.9 by increments of 5. Notice how it doesn't count 6.9 because 6.5 plus 0.5 is 7. And 7 is not part of this. You said to 6.9. So it only does to 6.5. Versus this one, 4 to 6, length 9. It separates them by moving every 0.25 it increases. Pretty logical. So go ahead and try this yourself. Create a sequential vector that starts at 1, ends at 100 by increments of 10. What would that look like? And create a sequential vector with 10 equally spaced elements from 1 to 100. So increments, equally spaced. Go ahead and do that. Okay, now you're going to pause me while you do that and play me when you're ready. Okay, so you can also replicate vectors. So this is when you want to generate lots of random data. So say there's like 3 options someone can pull from a bucket of balls, red, blue, and green. And we assign them numbers 1, 2, and 3, and we say there are 256 of each color. So then we would repeat this sequence 1, 2, and 3, or red, blue, and green 256 times. And what does this give us? Well, this gives us 1, 2, and 3 156 times, or 256 times. So say why would you do this? You would do this because say you're doing some experiment where you're saying what is the probability of pulling out a red, blue, or green ball when there are 256 of each color. Well, now you have your data set, right? This sequence function made your data set. So now you'll use a different function, such as a sample function, to pull random numbers. And then you would do that a certain amount of times and calculate the probability that you got. So go ahead and try this yourself. Pause me and play me when you're ready. Okay, combining vectors. So let's say we have 2 variables here, 2 objects, x and y. X is a vector that starts from 7 and goes to 4 by increments of 1. Versus y is a repeating vector of 9 3 times. So it's 9, 9, 9 versus this is 7, 5, 4, or 7, 6, 5, 4, 3, or no, 7, 5, 7, 6, 5, 4, right? So you can combine a vector into another vector, and this is why we assigned it an object, so we can easily do that. Otherwise we would have to put the function in each one of these things, and it actually doesn't allow that. So say we want a vector that has x as the first element, and as the last element, and y as the second element, and 10 as the third element. So you would simply put x, y, 10x. Now what is that going to make? Well, it's going to make x first, so 7654, then y, 999, then 10, then x, 7564. So let's see if that's true. 7654, 999, 10, 7654. So that's all it did. So go ahead and try this yourself. And we're going to try combining some things that we already learned in this lesson. So I want you to take these three variables, A, B, and C. B is not done yet. See, it's hashtagged. Define, so solve for the quotient as variable B. So variable B is the quotient of this. So define variable B as the solved quotient from what we did above, and then combine it and to read the hidden message. Combine the vectors in the orders of A, C, B to read the hidden message. Okay, so pause me and come back when you're ready. Filtering elements. So filtering is how we call a specific element within a vector. So let's first make a vector. We're making a vector that is called data, and it's 11 through 20. So what does that mean? It's going to be 11, 12, 13, 14, 15, etc. to 20. And it's increments of 1. Why? Because you use the colon function and nothing else. So what if you want to know the 9th element of this list and then the first element of this list? Well, you just say, you call the object, so data, put it in brackets. Brackets means you're referring to this object. And then you just simply concatenate 9 and 1, and it equates to what is the 9th element and what is the first element. Now, what if you want all the elements except the 9th and first element? Well, you do the same thing. You call the data set, you call the object, and you write your concatenated statement, which is you want the 9th and first one, but then you put a negative in front of it. And that negative says, I don't want the 9th and the first one. I want everything but the 9th and the first one. So, what will this be? What will spit out here? Well, what's going to spit out is the 9th and the first element. So, the 9th one is going to be like 19, right? I don't know. I can't do math. Or 20. And then the first one is going to be 11, right? And then this is going to be everything except 11 and whatever the 9th element is. 19. So see, there's no 11, there's no 19. And this one is only 19 and 11. So you can also, say you have a data set that's got like a lot of repeating things. Well, you can pull out unique elements by using the function unique. And all you do is you define your data set. So this data set is defined here as antiques, and then you use the function unique and with parentheses, and then reference your object, and there you go. So what are the unique objects here? Well, it's not 122 because there's 3 of them. It's not 12 because I see 2, and it's not 15 because I see 4. So it's only going to spit out 14. Oh, never mind. It doesn't just spit out 14. It spits out each number that is unique. So it's not going to give you 2 12s, 3 122s, 1 14, and 4 15s. It's just going to tell you 12, 122, 14, 15. Make sense? So go ahead and try it yourself. So create 2 vectors, alpha and beta, where alpha is a sequence from 1 to 20 by increments of 1, and beta is a sequence from 1 to 20 by increments of 2. Combine the vectors and print a vector that contains only unique values in the combined vector. So we're building on each other, building on what we're learning. So do that, come back when you're ready. So we can also table elements. So tabling means how many times is a unique element repeated. So this time, if I didn't want to count or my data set was too big and I wanted to know how many times this certain element was repeated, then I would simply use the table function. So print, and there you go. 2, 1, 4, 3. Boom. So the last thing I'm going to show you is that you can do vectorized operations to vectors. So let's say we have two vectors, j and k. So let's say we want to know k to the j for every element of k. So this will assign each element of k a corresponding value of j and compute said calculation. And since k is bigger than j will be repeated twice to complete the vectorized operations of k. So it's going to be 1 to the 2, 2 to the 3, 3 to the 2, 4 to the 3. And there you go. It was exactly that. So now try it yourself. Use the antiques vector, and I want you to take the natural log of each element in the vector and create a table with the calculated values and their frequency. So let's work through some examples. That's it for the lesson. So example 1, suppose P of A, or the probability of A, is 0.8 or 80%, and the probability of B is 0.6 or 60%, and the probability of A and B, that's what this U means, is 0.55. So now determine what's the probability of A or B. So A or B equals this formula. So we have been given P of A, P of B, and P A and B, which means all we have to do at this point is plug and chug. So we say PA, let's call it PA and B, equals P of A, which is 0.8, plus PB, which is 0.6, minus P and B, which is 0.55. So the probability of P or B is, oh, I didn't print, so it's not going to come up underneath. There we go, 0.85, but it also came up here. So number 2, compute the area of the shaded region below. So pay attention to exactly how I do this, because these are the problems you're going to do on your own. They're exactly like the ones I'm showing you how to do. So we need to know basic geometry and how to count and probability to do this. So let's call this square PA and this rectangle PB. So PA, its area is going to be the length times width, right? So from 0 to 4 is its width, and so that's 4, and from 0 to 4 is its length. So 4, so it's going to be 4 times 4. PB is a rectangle, so its area formula is width times length. So width is from 3 to 6, which is 1, 2, 3. Yes, is that correct? Yeah, 1, 2, 3. So that's 3 times from 2 to 6. So 1, 2, 3, 4. And then we have a P and B. So P and B. That's this little rectangle. The P and is what's intersecting between the two, right? What's both events. And so this is an area of 1 by 2. So 1 times 2. So now we want to know, so we want to know the area of the shaded region below. So the shaded region below is all of it. So we only want to know PA or B, or we want to know sorry, I am blanking for a second. So basically, we want to use this, and we want to use this, and then we need to subtract what's in the middle, so that way it's not counted twice. Does that make sense? So we're getting PA or B because it's PA plus PB minus PA and B. So it's P, A, or B. I'm going to name it something different because I have something named that already above. So this time we're going to just call it. So it's going to be PA times PB, or sorry, not times, plus PB minus PA and B, right? Okay, so let's do print PA or B and 26. Oh, that's wrong because it has to be a percentage. Or wait, no. This is just compute the area. So yeah, the area is 26. We're good. Okay, last example, guys. So Google this formula to know what all the variables mean, but you're going to kind of figure it out here because this is how you get mu, and you got to use mu down here. So you got to use 2 formulas. So this builds on it. So pay attention to this. So in the following table, so use the table to find the number mu. So we can simply do, because it's the sum of x times the probability. So you do x times probability, and then you sum up all those answers. That's what this means. So let's create 2 vectors. Let's create x. What? Okay. Yeah, x equals c is 4, 3, 2, 1. And prob equals 0.391, 0.288, 0.180, 0.141. And it's important that each pair is in the same position in the vectors. So we can do a vectorized operation first. So we can do, we'll call it xx prob, so x times prob, equals, how did we do vectorized problems? Well, all you can have to do is we want to multiply the 2 vectors together, so all you have to do is x times prob, and that's it. And then say you want to get the sum of all the answers that are the x times prob, so all we do here is we go mu, because this is going to be the answer to mu now, mu equals sum x prob. Let's run it. Okay. Let's print both of my things so it just comes up underneath it. Okay, let's run again. And boom. So the average is 2.929. That makes sense because 0.391, so basically 0.4, and basically 0.3 is 0.7. So it should range 70% of the time between 3 and 4, and 30% of the time between 2 and 1. So it's basically 3. There you go. And yeah. So that's how you find mu, and all these problems are for you to do, 4 through 7. When you're done, click knit, this drop down, click knit to Word. It's going to go to your working directory. It's going to create this, right? So this is everything we did. So everything I typed in here and everything that got printed is going to come out here. Now what you're going to do, you're going to say File, Save As. You're going to go to wherever the files are. And then you're going to say PDF, export. Because this doesn't let you save it and open it. It's dumb, it's weird. So then I can go to my files where I saved it. And there you go. And this is what you're going to submit to the Google Drive folder. Okay. I know that was a lot. Watch it again if you need. Email me if you have problems. Okay. Have a good night, y'all.